Okay, continuing where we left off, section 4.6. So we're talking about the energy levels, and then I was talking about the line spectrum. So the electromagnetic spectrum is a continuous spectrum, whereas the atomic spectra is a line spectra, all right? And how was that line spectra obtained? So you're heating up an element, and what would happen is, suppose you have an electron at n equals 1, all right, and it absorbs the energy from the heat, and then it gets so much energy and it goes to the next higher level, say n equals 2. But it's unstable there, it doesn't belong. So it comes right back to where it belonged. And all of that excess energy that it absorbed as heat is then given out, it's emitted out. And when it's emitted out, it's emitted as light. All right. Now, if this light happens to fall in the visible spectrum, then we are able to see that. Like for barium and sodium and copper, and various other elements, when you do the flame tests, where they all give out a characteristic kind of color to the flame, and that's because the emitted light can happens to have the energy change that is involved with that emitted light happens to fall within the visible region. At other times it doesn't. It might fall in the infrared region, at which case we won't be able to see it. Okay. So this energy difference between n equals 1 and n equals 2, then that emitted light corresponds to that energy difference. And that's how why you see the atomic spectrum as line spectrum instead of a continuous spectrum. Again, here, if it has gone from n equals 1 to say n equals 4, all right, and then again it comes out, that emitted light is now at a higher energy, all right, because it's gone to a much higher level than over here, all right. So that will be emitted in a different region, and you'll see that as a different line. So the sublevels, we talked about sublevels. The order of energy for the sublevels is S is less than P is less than D, and D is less than F, all right? S is associated with 1 orbital, P is associated with 3, D has 5 orbitals, and F has 7, all right? That's why their energies are different, because P has 3 orbitals, and remember, each orbital can have 2 electrons, all right? So P can have a total of 6 electrons, D can have a total of 10, and F can have a total of 14, all right? So more electrons, it's able to accommodate more energy, okay? So S is the lowest. It's only able to take in 2 electrons in its sublevel and its orbital. And the orbital names are the same as the sublevel. So you have the s orbital, and then the p orbitals are aligned according to the axis. So it's px, py, pz. And then you have the d orbitals, and then you have the f orbitals. All right. So 5d and 7f orbitals. Okay. And 3p orbitals and 1s orbital. The number of sublevels is numerically the same as the energy level. So n equals 1 has 1 sublevel. N equals 2 has the S and the P. N equals 3 has S, P, and D, 3 sublevels. N equals 4 has S, P, D, and F, 4 sublevels. Okay. So you can see that N equals 1 has 1 sublevel, S, and then 1 orbital, which is also S. N equals 2 has 2 sublevels, and it has the s orbital, the s sublevel, s orbital, and the p sublevel, which has 3 orbitals, px, py, and pz. N equals 3 has got 3 sublevels, the s, p, and d, and the associated orbitals, s orbital, the 3p orbitals, and the 5d orbitals. And then n equals 4 has got s, p, d, and f, 1 s orbital, 3 p orbitals, 5 d orbitals, and 7 f orbitals. Okay, so n equals 1 can hold 2 electrons, n equals 2 can hold a total of 8 electrons, n equals 3 can hold a total of 18, and n equals 4 can hold a total of 32 electrons. The shape of the orbitals. S is a spherical type of shape, all right? So it's kind of like diffuse. This is kind of a diffuse region in which you find the electrons in an s orbital. The first s orbital in the first level, n equals 1, is a small sphere. Now the 2s is going to be larger, and then the 3s is going to be an even larger one. Okay. So the higher they are in energy level, all right, that means it's going to be larger, the size of the orbital. In the p orbitals, the p orbitals have got 2 lobes, all right? They're described as being dumbbell shaped, all right? And those lobes are aligned according to the axis x, y, and z, okay? Now, in a p orbital, if you have, each p orbital can hold a maximum of 2 electrons. Remember, a single orbital can only hold 2 electrons, all right? And so those electrons will be aligned in opposite directions, all right? So they have opposite spins, as you can see here in this picture, all right? There will be one electron spinning clockwise and another spinning counterclockwise. Okay, so here you have the p orbital, px, py, and pz. Okay, and there are 2 electrons per orbital. And then the d orbitals are double lobed, and it becomes even more complex. Okay. All right, Pauli's exclusion principle. This is a principle that states that when you have a single orbital, it can't hold any more than 2 electrons, all right? So if you imagine the electron hotel instead of the planetary system, right? So in the first level, you have, say, a suite, all right? The sub-level is like a suite. So you have the S room, and each room has only 2 occupants. So the electrons are the occupants. So the maximum capacity of a room is 2, all right? When you come to P, it has 3 rooms. So again, each room can only accommodate 2 occupants, all right? So again, the total capacity is 6, but again, a single orbital is always 2, no matter if it's S, P, or D. Hund's rule states that if those orbitals are of the same energy, like in the P sublevel, then first every room or every orbital must be filled before you can have double occupancy, all right? So they go in single file, and then the pairing up starts, all right? So if they are aligned in the same direction, they would repel each other. Therefore, they have to be aligned in opposite direction, opposite spins. So this is called as the magnetic spin, or the magnetic spin quantum number, to be more precise. And electrons are represented as arrows, just because of the fact that it's easier then to show the alignment. So therefore, opposite spins, meaning there is an arrow pointing downwards and another pointing upwards. So the maximum number of electrons that can fill a sublevel depends on how many orbitals are present in the sublevel, all right? One orbital means only 2 electrons. P has 3, therefore it can have a total of 6. D has 5, so it can have a total of 10. And then F has 7, so it can have a total of 14. Right? So N equals 1, 1 sublevel, 1s. Number of orbital is 1, so the number of electrons is 2, so total is 2. If you come to 2, energy level 2, then it has 2p and 2s. 1 for the 2s, 3 for the p, and then that's 3 times 2, so 6. 6 plus 2, 8. All right. And then you come to the third, it's s, p, and d. 1 orbital for s, 3 for p, 5 for d. So 2 plus 6 plus 10, that gives you 18. And then you have S, P, D, and F for the fourth level. So 1, 3, 5, and 7. So that's a total of 32. Which of the following elements are likely to have electrons in the 3p sublevel? All right, now those sublevels are corresponding with the period. All right, so carbon and oxygen are in the second period. Silicon and arsenic, however, are in the third period. So only silicon and arsenic would have the 3p sublevel. All right, so that is the end of this section 4.6. Homework is the questions 4.1, 4.41 to 4.48 on pages 126 through 127.